Okay, so this is going to be our first lesson. We're going to be looking back at what we were looking at before the earthquake. so, let's just jump back into it. This is going to be a theoretical lesson. I'm trying to keep these as short as possible so that you guys don't lose your attention, that I don't lose your attention. So let's get started right away. So this thing, what the topic for this lesson is, oh, sorry, okay, there we go. Motion along a straight line. Okay, so we're going to be talking about motion along a straight line. This completely means this is equal to one-dimensional motion. Okay, remember that we'll be talking about vectorial quantities. Okay, kinematics is all about position, it's all about velocity, and it's all about acceleration. And all of these, well, not necessarily not position but displacement, all of these quantities are vectorial quantities. That means that they both need to have magnitude and a direction. In this case, since we are talking about one-dimensional movement, there are only two different directions that we can move. Well, there's an infinite number of directions, but we'll basically just be talking about two directions. We can either go up or down, or we can either go left or right. Okay, so these are the directions that are going to be basically the ones that we are analyzing in one directional motion. We have to establish what is the sign of each one of these directions. Normally, the up direction is the positive direction, and the down direction is a negative one. Also, left is negative and right is positive. It doesn't matter what direction you decide to use as positive, as long as you keep your calculations with these signs. For example, if I were to define motion along a straight line of a vertical throw, and I define positive to be downward, then I would have to make sure that every single one of the things that I use to calculate the position of my, whatever we throw, if we are going downwards, we need to establish that as a positive direction because we established it from the beginning. So we need to be coherent with what we established at the beginning to be positive and negative. Okay, so since displacement and velocity are both vectorial quantities, we need to know the direction. The direction is going to be implicit in the sign. Okay, so if we have a positive velocity in a vertical throw, that means it is going upwards. If we have a negative velocity, it means we are going downwards. If we have a positive velocity in a horizontal motion of a projectile, we know the positive is going to the right and negative is going to the left, using this specific notation, right? So if we define things to be like that, then we're not going to have any problems whatsoever. Okay, so since we are talking about motion along a straight line, we can talk about one specific subtopic, which is called free falling. Okay, so free falling bodies. So this subtopic will be covering two specific examples of free falling bodies. One in terms of vertical throw, and the other subtopic will be free fall. These are subtopics, but they are basically the same thing. We'll be using the exact same equations in all of these in these two topics. This type of movement, one thing that is very important when we talk about free falling bodies, so when we talk about this free falling bodies, is that the only force that governs this type of movement is gravity. This is ideal, okay? This is an idealization. When you throw something upwards and it starts falling on its own, then the only force that it's actually accelerating it is gravity. We know that there are other forces that prevent that object to fall freely, right? But we are not going to be taking those forces into consideration. One of those forces, for example, would be air drag. Air drag. Air drag is the resistance that the free falling object is going to feel once it's falling freely through the air. It's basically particles of air resisting the movement. Therefore, it's a force that is opposing gravity. But right now, we will not be looking into this. Okay? We will be looking only the idealization that on free falling bodies, the only thing that governs how things fall, how they free fall, is gravity. And this was proved by Galileo. Well, it wasn't proved by him, it was theorized by Galileo at first. And what this original statement says is that it doesn't matter how heavy the object is, it will always fall at the same rate. It will always have the same acceleration. That's because gravity is the only thing that is pulling that body down. Okay? In theory, I don't know if you guys remember, but we have this equation here, m1 times m2 over r squared. In theory, the mass does influence how fast a free-falling body will fall. Look at this. It depends on the masses. But remember that this mass right here is the mass of the Earth, right? So the mass of Earth. Since this mass is so huge in comparison to this one, it doesn't matter what number we put here, the force will be basically kind of the same, okay? And thus the acceleration will be basically the same. Okay, so it does relate, the force that pulls the body down does relate to the mass of the object. It does. But since it is being pulled by such a massive amount of mass due to the Earth, since it's being pulled by the Earth, it doesn't matter how heavy this object is, it will never compare to the mass of the Earth. Therefore, this thing becomes negligible. Okay? So let's look at a video, and we'll finish with this video. Let's see if I have it here already. Okay, so let's look at it. It's pretty fun. It's only 4 minutes long, and we'll be done with today's lesson.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. it takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop.
PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Look at that.
They came down exactly the same. Wow.
Look
how they hit right there.
Exactly.
Back on the side.
Exactly the same.
Feathers don't move, nothing. Look at that.
That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this: the reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the earth. So he concluded they weren't.
Okay, so I hope you guys enjoyed that video. This is basically to show that free-falling bodies, in theory, fall at the same time. It means that the only force that is acting upon them is gravity. Okay, we saw that that doesn't necessarily happen in the real world. Why? Because there is something called air resistance or air drag. This thing slows down the feathers as they start to fall. They have a higher drag, therefore they resist falling in comparison to the ball that has a lower drag that falls freely. So that is basically it for today's lesson. Okay, so this is just a quick recap on what is motion along a straight line. On the next lesson, we'll start doing some calculations. Remember, every single calculation that we do will be an idealization, right? That means that we will not be considering air drag in our calculations. We will be only considering the acceleration that is a product of the gravitational force that is pulling the objects down. Okay, so right now, only motion along a straight line in terms of vertical throw and free fall will be only considering the force of gravity, nothing else. Okay, so thank you for watching the video. Subscribe to the channel, give me your likes. Nah, I'm just kidding. I hope you guys enjoyed this, and I'll show you the next video in a minute. Okay, goodbye, guys.